Ever wondered how a piece of sports equipment unleashes the power to shatter records? Modern tennis rackets contain over 20 layers of carbon fiber precisely arranged for perfect balance, using materials originally developed for aerospace. In this video, we're taking you inside the factories where today's high-performance rackets are born. You'll meet the craftspeople who meticulously construct these engineering marvels and witness their passion firsthand. You'll see the transformation from raw carbon fiber sheets to the finished product that can withstand forces of over 3,000 pounds when professional players strike the ball at speeds approaching 150 miles per hour. Before we dive in, please do subscribe to our channel. Ever wondered what's inside the racket that helps professional players hit with such power and precision? The answer begins with materials you wouldn't expect to find in sports equipment. The journey starts with carbon fiber, the same material that forms the backbone of Formula One cars and commercial aircraft. This remarkable substance arrives at racket factories in large rolls that look nothing like the finished product you see on store shelves. Modern racket manufacturing balances competing requirements, creating frames that are lightweight for fast swings, while remaining durable enough to withstand thousands of high-impact hits. This delicate balance requires precise engineering to achieve flexibility for shock absorption alongside stability for control. At cutting stations, workers operate computer-guided machines that slice carbon fiber sheets into specific patterns, with accuracy to within 0.1 millimeters. This precision matters because even tiny deviations affect performance. The machines cut different shapes for each section, wider pieces for the head, narrower for the shaft, and specialized cuts for the throat area where stress concentrates during play. Following this meticulous cutting process, technicians arrange these carbon fiber pieces in specific orientations, much like assembling a high-performance sandwich with each layer serving a distinct purpose. The complex structure of 15 to 20 sheets includes some layers running lengthwise for longitudinal strength, while others positioned diagonally for torsional stability. This architectural precision prevents the rackets from snapping during powerful serves and resists twisting when the ball hits off-center. Next, workers coat the layers with epoxy resin as a binding agent, creating pre-impregnated carbon fiber that's tacky and moldable. This material wraps around a frame mold in a process called layup that determines the racket's fundamental characteristics. Different models use varying layup patterns to achieve specific performance profiles for power, control, or feel. The wrapped mold then enters hydraulic presses heated to exactly 250 degrees Fahrenheit. Under intense pressure and heat, the separate layers transform into a solid yet hollow structure. This curing process takes 20 to 45 minutes, with temperature remaining perfectly constant to prevent weakening the carbon fiber matrix. During this stage, manufacturers often insert foam cores or stabilizing bridges inside the frame to enhance stability without adding significant weight. These internal structures dampen vibration and prevent frame deformation on impact. The emerging frame undergoes numerous precision processes before it's ready for stringing. Quality control specialists examine each frame for weight consistency and structural integrity, rejecting any with visible defects or those falling outside strict weight tolerances. Sometimes as little as 2 grams difference from target specifications. Only frames meeting these exacting standards advance to become the precision instruments that players rely on in competition. You might think drilling holes in a racket is simple, but the location of each hole can change the entire playing experience. Those small holes determine how your racket feels and performs, and manufacturers use technology you probably wouldn't expect to create them. After the carbon fiber frames cool down and pass their first quality checks, they move to specialized drilling stations where the real precision work begins. Like a surgeon making precise incisions, the next phase transforms a hollow frame into something that can hold strings. Computer-controlled drilling machines prepare the racket for its most important component, the string bed. The pattern, size, and angle of these string holes directly affect performance. Holes placed farther apart create more power with reduced control, while closer holes provide accuracy at the expense of that satisfying pop when hitting the ball. Tennis rackets present a complex challenge for manufacturing teams. A typical tennis racket requires up to 76 precisely positioned holes, from 16 to 18 main vertical strings and 19 to 20 cross-horizontal strings. These holes must align perfectly on both sides of the frame with precision measured in fractions of a millimeter. A professional player once tested a prototype racket that had a barely perceptible 0.5 millimeter misalignment. After taking just 3 shots, he returned the racket, remarking that it felt completely wrong. Such extraordinary sensitivity highlights why manufacturers invest heavily in advanced optical recognition systems. These systems scan each frame with high precision, generating digital models that capture even the slightest variations. The machines then automatically adjust to ensure perfect alignment, meeting the exacting standards demanded by elite athletes. Badminton rackets demand even more care during drilling. Their extremely thin frames, sometimes just 7 mm in diameter, require specialized micro drills and slower drilling speeds to prevent structural weakening. A single misplaced hole can create a weak point that snaps under competitive play impacts. After drilling comes the installation of grommets, small plastic tubes protecting both strings and frame. These unsung heroes prevent strings from cutting into sharp carbon fiber edges while allowing proper movement during impact. Modern tennis grommet systems include shared holes and channels that let strings move slightly upon ball contact, creating a trampoline effect that adds energy while enhancing spin. The drilling pattern creates what manufacturers call string bed density, determining power, control, and spin generation. Open patterns with fewer cross strings produce more power but less control, while dense patterns offer precision with less free power. This explains why professionals choose different string patterns based on playing style and court preference. Paddle rackets take a completely different approach. Instead of creating hollow frames for strings, production involves drilling holes directly into solid core materials. These holes reduce weight and create aerodynamic properties, affecting both ball rebound and how the racket moves through the air during quick net exchanges. The racket that arrives in your hands has survived a gauntlet of tests that would destroy lesser equipment. What you see as a finished product has endured impact forces that simulate years of professional play compressed into just minutes. After drilling and grommet installation, rackets enter the finishing department, where they transform from raw carbon fiber frames into the colorful branded products you see in stores. At this stage, they still look nothing like the glossy equipment displayed in tennis shops. Manufacturers face a critical challenge in this phase. They must balance aesthetics with performance. Adding paint, graphics, and protective coatings changes the weight and balance of the racket. These specifications must remain within 1 to 2 grams of the target weight, as every gram matters in a product where performance depends on precise engineering. The painting process resembles a chef layering flavors in a signature dish. Automated spray systems apply multiple thin layers rather than fewer thick coats. Each layer adds microns of thickness to maintain the racket's carefully calculated specifications. First a base coat sealing the carbon fiber, then color layers creating visual design, and finally clear protective coating shielding against UV damage and impacts. These systems ensure even application across the frame, preventing heavy spots that would unbalance the racket. For graphics and logos, water transfer printing has revolutionized the process. This method allows complex patterns to conform perfectly to the frame's curved surfaces by floating printed films on water, then dipping the racket through this film. The pattern wraps seamlessly around the entire frame, creating detailed gradient effects without affecting performance. Handle construction varies between racket types. Tennis rackets receive molded pallets with synthetic grips for sweat absorption and cushioning. Badminton rackets use cork or thinner synthetics that prioritize weight reduction, while paddle rackets feature ergonomic, textured handles for grip during quick exchanges. Before stringing, rackets undergo sophisticated testing. Frequency analysis machines measure vibration patterns to detect invisible internal defects. Impact testing simulates thousands of ball strikes by applying forces exceeding 40 kilograms to verify durability without deformation. Quality standards are so stringent that approximately 20% of frames get rejected for often microscopic flaws. This high rejection rate contributes to premium racket pricing. You're paying for the perfect ones that survived all testing phases. The final step is the stringing process. Automated machines tension each string precisely to specifications, starting with vertical main strings, followed by horizontally woven cross strings. With strings installed and final inspections complete, the racket transitions from raw material to high-performance equipment, ready for packaging and shipping, the last step before reaching your hands. The racket in your hand represents the culmination of aerospace engineering, materials science, and precision manufacturing. What began as simple carbon fiber sheets has transformed into equipment that can withstand forces exceeding 3,000 pounds at impact. This is engineering you can hold. The shift from wooden to metal and then composite rackets represents a major technological leap. Each material advanced the game distinctly. Today, smart technology and 3D printing are revolutionizing racket production. Next time you pick up a racket, see the marvel of engineering with decades of innovation built into every frame. Will you appreciate the hidden technology behind each powerful swing? Do like the video and subscribe to the channel. See you soon in the next episode.